Hello, I am Carlos Esquivia from Miss Jacome's Geometry class, Section 2, and my video lesson today will be on proportions of triangles. The first thing to understand with proportions of triangles in relation to geometry is what is a proportion and what is a triangle. Well, a proportion is a part, share, or number considered in comparative relation to a whole. In math, that would be the relation of one thing to another in terms of quality, size, or number, aka the ratio. I'll just take, for example, the top half of this whiteboard. Now, the rectangle to the left has a length of 4 and a width of 2, and the one on the right has a length of 2 and a width of 1. Now, these are not drawn to scale, of course, but these are just hypotheticals. Now, these are proportional, or have the same proportions, because one side is 2 times the length of the other, and opposite sides are congruent. So, in other case, the quadrilateral, or the figure, was just dilated. So they have the same proportions, yet they are different sizes. Now, a triangle, on the other hand, is a geometric figure with 3 sides and 3 vertices. Now, the first theorem that we're going to get into, because there are a few, is Theorem 7.4, which is the side splitter theorem. And it reads, if a line is parallel to one side of a triangle and intersects the other 2 sides, then it divides those sides proportionally. What does this mean? This means that if line RS is parallel to XY, then the sides XR and RQ are if they're divided, are proportional to YS and SQ. Now, how could you actually determine this? Well, you can determine this by giving a short example. So let's say these are the midpoints, and SY and QS have the lengths of 3, and XR and RQ have the lengths of 2. So the fractions will be 2 over 2 is equal to 3 over 3, like so. And of course, 2 over 2 is 1, and 3 over 3 is 1, meaning that they are equal to each other, which they are, and that means they're proportional. Now, the corollary to this theorem, and the corollary being a proposition that follows one which is already proven, looks something like this. It's 3 parallel lines with 2 transversals, and this is almost the exact same layout as a triangle, just without the some vertices. And the corollary states that the length from AB to over the length to BC is the same ratio as the length of WX over XY. And this is proven through the previous theorem, meaning it doesn't have to be proven by any other postulate, theorem, or proof. The next theorem that we'll be looking at is the triangle angle bisector theorem, Theorem 7.5, and it states, if a ray bisects an angle of a triangle, then it divides the opposite side into 2 segments that are proportional to the other 2 sides of the triangle. Now, here's a diagram to show. This means that segment CD and segment D over segment DB is proportional to segment CA over segment BA. So the first example that I'm going to give is for the triangle angle bisector theorem, and it looks like this. What we have to find here is x, and we can find x by using the proportions that from the theorem, the formula, and it looks like this. The proportions are 5 over 12 equals 3.5 over x. We cross multiply in order to get 5x equals 42, 42 being 12 times 3.5. With that, we divide 5 from both sides, and to get x equals 42 over 5, and we simplify it by making it x equals 8.4. And always remember to label. In this case, there was no unit of measurement, so we will just use units. Now, a thing to remember is to always check your work in order to make sure that your answer was accurate. And for this question, we could check our work by substituting the value of x back into the cross multiplication. An alternative thing to do is to substitute it back into the original fraction, but I prefer this way. And it's clearly seen that 12 times 3.5 is equal to 42, as well as 5 times 8.4, which is also equal to 42. For my next example, it'll be on the side splitter theorem, and it would look like this. Now, you need to simply find x, and you find x by using the same proportion ratio as you did within the theorem. It's very similar to the previous example, the triangle angle bisector theorem, but it's slightly different because instead of using two adjacent sides, you're using segments that connect to make the same side. And it would look like this. Here's how you would solve it. 6 over 3 equals 10 over x. To find x, you cross multiply. 6x equals 30, 30 being 10 times 3. X would equal 30 over 6 because you would divide 6 by both sides. And then you would find out that x equals 5 when you simplify. And in order to check that, you could either put it back into the fraction or you could go through the multiplication yourself. I personally like the right one again. And for my next and final example of this topic, it'll be of the corollary, and it looks like this. It's another one where you have to find the variable, but this time the numbers aren't actually as divisible by each other as they would be in other problems. And of course, it's not drawn to scale. You'd solve it like this. 12 over x equals 18 over 37. Cross multiply, and you get 18x equals 444. X equals 444 over 18. X equals 24.6, and it's a repeating 6. And to check that, you just multiply, cross multiply again, but you substitute the x with the 24-point repeating 6, and you would get 444 for both equations. I hope this video was helpful in you understanding the concept of proportions of triangles and understanding it a little more in depth with the theorems and the corollary. I hope to never do this again, and have a wonderful day. Move. Take, for example, these two squares. They're actually rectangles.
Hit it!
This shit that ice cold, Michelle fight for that white gold. This one for them hood girls, them good girls, straight masterpieces. Stylin', wildin', living it up in the city. Got Chuck's on with Saint Laurent, got a kiss. kiss myself. I'm so pretty. I'm too high.